Hello, everyone. We are presenting today the PhD candidate at Utrecht University, Professor Robin. His work is on dynamical systems and theoretical physics. He had the best master thesis in 2021 for his thesis entitled The Fractional Calculus Equation, and his research shows that we can apply these complex formulas of fractional calculus to unify and describe many different states of matter, such as liquid glass, marginal glass, and even the recently discovered time glass through a single equation. So we thank you, Professor Robin, for accepting, for submitting your work to this symposium. And we are presenting your work entitled Fractional Calculus in Quantum Dissipative Systems. So the next is yours.
Thank you very much. Yeah, so the work I will be presenting here is mainly done under supervision of Christiane Murray Smith, who gave a talk here yesterday. Um, all right, so let's get into it. As said, I am mainly doing physics, but since you are a mathematician's audience mostly, I will assume you know quite a lot about the fractional derivatives, and I will try to give you some intuition for how these can be applied in our field. So, okay, first of all, of course, we know there are many different definitions of fractional derivatives, and an important question for applications is, of course, which one to use. Um, well, so here, first of all, we see some examples. So here with the Riemann-Liouville derivative acting on a function t squared, and we have the integer order derivatives as the solid lines, and then you see the half order derivatives in between. And of course, these all feel quite natural, except perhaps when we go to this 2.5 derivative of t squared, we get this strange line going up. It is 1 over square root of t. And, well, physics might not actually want this line to exist. And so we have some choices there. So in this case, this is for the Riemann-Liouville derivative, as you can see in the top right here. But we could interchange this order of the integer derivative, and we find the Caputo derivative. And if we do so, then this 2.5 derivative will suddenly be zero because of the third order derivative. And so that's actually something which nature seems to prefer. And so therefore we will mainly use this Caputo definition, where we have this base point, and typically it depends on the situation, but you would put this either at zero or at minus infinity. And at minus infinity, we also call this the Liouville derivative. So, okay, why do we do these fractional derivatives in physics? Well, first of all, they are non-local operators, so they can provide us with a sense of memory. Of course, we can basically interpret this as an integral over time, over history. That also means we have a preferred direction for our integrals, right? We don't want things to depend on the future. And yeah, some previous applications, we have this groundwater protein folding. We saw some other applications earlier in this symposium. So, okay, let's get into our application. And for this, we will look at quantum dissipative systems. So to give you an idea, we are talking, for instance, about an electron moving inside of a metal. So there's many different particles interacting with each other, and somehow through all these interactions you lose energy to the environment. Now, quantum mechanically, this is quite hard to describe because if you do a Hamiltonian formalism, energy is conserved. So if you want to do this, you have to include the entire environment in your description. And of course, that becomes very complicated very quickly. So you want to simplify this down as much as you can. And well, here we have some example where you have a particle inside a glassy system, and you see the free energy landscape. It's very chaotic. There's many different of these bumps and minima and name it everything. And we will try to ignore all of these small details. And basically, we will say, well, let's just assume there's very little energy available. Then it's very hard to go over one of these bumps. And therefore, we can essentially describe all the different minimas as separate quantities. And this is how we will get to basically the simplified picture of Cabrera-Leggett, where each of these minimas we will describe as a harmonic oscillator. This is x squared. So this will describe the minima very well, unless you have a lot of energy, but we will look at the low energy case. So this is the Caldera-Leggett model pictorially. You have your system of interest in the middle, and then this is surrounded by this big set of harmonic oscillators, which we couple to the system of interest. And what is nice about this system is that doing it in such a way, we have harmonic oscillators which are x squared, we do linear coupling, and this allows us behind the scenes basically to complete the square in some Gaussian integrals and basically integrate out all of these degrees of freedom and be left over with an effective action on the system. And from this, we can calculate equations of motions and all of these things. So that's very practical. And as said, this was done by Caldera-Leggett. Caldera is, of course, a Brazilian physicist. So, yeah, let's get into the first example. This is how it was originally done in well, 19 something. It's behind the button for me, sorry. Okay, so, well, we will consider basically a free particle inside one of these harmonic oscillator baths. And if you do this calculation, I will spare you the details. But the one thing which is very important is the bath spectral function. It's this object J of omega. And it's the imaginary part of the retarded susceptibility of the bath. And in human terms, it is basically the if you shake the bath at a certain frequency, how strongly will the bath push back? Okay, so it's basically a Fourier analysis of the modes in your bath. Now, typically this is assumed to be ohmic, but I want to be very clear. This is purely an assumption. This object is something which can be measured, but it's quite difficult in practice. There's large error bars. So it's just kind of hard to know what it should be, but we know that it is there. It's not something which is mathematical or so. It's really unobservable. But if we assume it's linear, of course, one of the most simplest assumptions, then we can derive this Langevin equation, which was actually already known before, but it was derived phenomenologically, so based on intuition instead of derivating, right? The Langevin equation, we have it here. There's mass times acceleration, there's eta times the velocity, which acts as a friction, and then we have some random noise. And I'm sure you all know at least a bit about Brownian motion, where you have this random motion going around. And, well, this is very well described, for instance, by a large particle inside of a fluid. And, well, finally, one thing which I want to point at, in equilibrium, we have fluctuation dissipation theorem. And this essentially relates two quantities, the fluctuation and dissipation. The fluctuation being this random force over here. And the size of the random force you see here, this eta, it comes back in the size of the friction term. So these two quantities, they are typically related, and that will be important for later. Because what we did in our research is go beyond the linear regime. So we assumed a subohmic spectral function, which is on the right here. So it's eta omega to the power s, with s between 0 and 1. And if you do so, then you can derive what's known as the fractional Langevin equation, where you have, again, the mass times acceleration, but now your friction is suddenly an S-order derivative. And this was done way before by Erik Lutz, who I assume most of you might have heard of. However, we did something more, because if you assume fluctuation dissipation, then this random noise over here will turn into a colored noise. And if you do so, that's still, of course, very interesting, but you will see quite standard anomalous diffusion results. But we wanted to find some out of equilibrium stuff, namely with glasses. And so for that, we have to go out of equilibrium. And we did this by applying a thermal gradient across the bath. So essentially the gradient, well, there's different temperatures in different parts of the bath. And that means that the fluctuation dissipation theorem no longer holds. And we can actually tune this gradient in such a way that we can keep the white noise over here, so delta correlated instead of a power law. And this is very important for what we are about to see. So yes, here is the mean square displacement. So let me first define what I mean if I talk about the glass. Of course, we have the windows in our houses. But for physicists, a glass is actually right here at the top. It's a very crude definition, but it's basically an amorphous solid. So it's something which is solid, but it doesn't have a clear structure between the atoms. And then again, the solid, just to define this in the mean square displacement context, that means that it becomes constant. Because the mean square displacement basically tells you over time how far can a particle move through my material. And so if this becomes constant, then it means it is bounded to a certain box. Now, what you can see over here is the calculated mean square displacements for different values of the fractional derivative. So on top, we have the integer values, the regular cases. And of course, for s equal to 1, you get your regular Brownian motion, which is a liquid. However, for s equal to 0, you already see some surprising things. We get the regular ballistic behavior at short terms, but now at long times, we see these oscillations appearing. And these oscillations, they are actually quite expected, because this s equals 0, it's a 0-order derivative for the friction term. So your friction becomes just eta times x. And this is effectively a harmonic potential. So we have a driven particle in a harmonic potential, so this starts oscillating, and that creates these steps. Now, if we go in between, we get the actual fractional derivatives. And what you see, if you lower s starting from 1, then this exponent here will lower and lower and lower until eventually at the half it becomes logarithmic, and below a half we find that it becomes constant. And so here we see the typical picture of a glass, because we have a microscopic liquid, but our mean square displacement is saturating, and therefore it's a solid. So this is what we would typically say to be a normal glass. Now, if you lower it even more, then you see that actually the mean square displacement starts picking up a few of the plateaus that we saw in the marginal glass case. And this is very interesting, because now we have this periodicity from the marginal glass, but we are still in the solid phase. So we kind of get the best of both worlds. And this reminds us very strongly of a concept which is known as time crystals, which was thought of by Frank Wilczek, a Nobel Prize winner. And this is about spontaneous time translation symmetry breaking. So this feels like it's a kind of perpetuum mobile, in the sense that without any active pushing, we start breaking the symmetry of time, kind of similar to how a swing would suddenly start moving back and forth. Now, quantum mechanically, it turns out this is possible under certain situations, which is why it made the cover of Scientific American. But this time glass is kind of a similar thought, but then inside glasses instead of crystals. So we have a glassy phase here, which exhibits this spontaneous time translation symmetry breaking. Now, one last comment about the time glass is that what you can clearly see in these figures is that this S, the order of the fractional derivative, is actually able to unify all these different phases of matter into a single equation. So this is a very powerful tool in order to unify different theories together, and perhaps even, just like the time glass, find new phases in between. Now, we can zoom in a bit on these phases. Here you see for very small values of S, and you see that the smaller S gets, the more of these plateaus we find. Now, the periodicity is also well known. It's given by this over here, pi times m over eta to the power 1 over s minus 2, 2 minus s. And yeah, it's, well, we can just see also here in the linear plot that this is very well followed. Now, let me just convince you very quickly. There are some experiments on marginal glass, and I think here you only see the increases between the plateaus, but they have some strong evidence that actually they might have measured a time glass, even though at the time they thought it was a marginal glass. But they only measure 4 plateaus, and so it's probably a time glass. Okay, so let me go on to the next bit, because this is where we actually derive a new equation with fractional derivatives. So in magnetization dynamics, we're talking about spins quantum mechanically, and these spins, they rotate under the effect of a magnetic field. So here you see what's known as the Landau-Lifshitz-Gilbert equation, and this is essentially how spins move quantum mechanically, although this is the classical limit of it, so it's a bit simpler. So what you see, there's certain effects. So first of all, we have spin precession, where if you apply a magnetic field, then a spin will start precessing around it. Then there's Gilbert damping, which will slowly align the spin to the magnetic field. And finally, we have thermal fluctuation. Now, again, this equation was first derived phenomenologically, but you can also do it through the Caldera-Leggett formalism if you use a thing which is called Keldysh theory. Now, that's quite far beyond the scheme of this talk, but its core idea is very similar, where you also get the spectral function, you assume it's linear, and finally you get the Landau-Lifshitz-Gilbert equation. Now, again, we assume that it is nonlinear, and it will not surprise you at this point that we find this S-order derivative here. The big difference in this case, it's a Liouville derivative, so it starts at minus infinity. Okay, so this is a new fractional Landau-Lifshitz-Gilbert equation. I would be very interested if some mathematicians could examine this equation a bit more, but we've already studied it a little bit ourselves. So, okay, we have this equation, and the question is essentially what changes. And it's quite a hard equation to solve, of course. So we apply what's called ferromagnetic resonance. And this is where we apply a rotating magnetic field, and we wait for a steady state and basically see how far is the angle of the spin compared to the z-axis. And what we find is that the resonance frequency actually shifts according to the value of S. So you see here for subohmic S, you find that it shifts to the right, and for subohmic S, it shifts to the left. And in this plot here, you can see the numerical values in the red dashed lines, whereas we have our analytical approximations in the black lines, and you see they match up very well. Now, in terms of applications, this is also quite interesting. We can have very stable systems for these subohmic ones, whereas we can have very volatile systems for the superohmic case. So that would be nice for either data transfer or signal transfer. But the main interesting bit is that these are actually observables which can be measured. So instead of assuming this linear spectral function, we can just measure in practice what's the value of S, and that will basically give you the correct equation to use for the dynamics. Now, finally, I want to do one quick shout out to this paper, which we did with a student of ours. And this is an alternative model to derive fractional derivatives. So as you saw, we always had to assume that the spectral function was nonlinear, that it's non-ohmic. But actually, it turns out this is not a necessary assumption. What you can also do is assume that the coupling between the bath and system becomes fractional, so it includes a fractional derivative. And in that case, we showed that you can derive this Liouville fractional Langevin equation. And what's very nice about this is that it's even more flexible in the parameters. So you can find a very wide variety of physical regimes, which you can see in this picture at the bottom. So you can find superdiffusion, subdiffusion, saturation, all these things. So finally, for conclusions, we use the Caldera-Leggett model, and we can describe non-ohmic dissipative systems. They have these fractional derivatives as a friction term. Liquids can be unified with glassy states using the fractional derivatives order. And we have the first derivation of a time glass. Magnetization dynamics can be generalized to this fractional Landau-Lifshitz-Gilbert. And it provides a way to determine actually this ohmicness, the value of the fractional derivatives. And finally, we have this fractional coupling, which is an alternative method. And with that, I would like to thank you.
Please turn on your mic, Vanterle.
Robin,
We have an echo.
Robin, okay?
Yes, it's okay.
Yes, okay. Thank you presentation, the excellent lecture, and now some comments and questions about the presentations. And Stefania, good morning Brazil, good afternoon Europe. Rubens, bom dia, good morning.
Yeah, if there are any questions, I'm happy to answer. I cannot answer in Portuguese, unfortunately.
Good morning. Good morning too. And many people, good morning, good morning, good morning, and good morning too, and good morning. And good morning, Camila Lima. I don't know. And they have two questions about the presentations and about the quantum mechanics. And the first questions about the Rubens Kamal. Excellent talk, congratulations. What are next steps? I already linking the super diffusion part.
Thank you. Yeah, so for next steps, we've tried several things also to apply fractional derivatives to fractals. Of course, that's very much what Christiane has been interested in also. But actually, it turns out that there you might also need this concept of fractal derivatives. So we've been looking into many of these different types of operators and seeing how can we basically use them to simplify all these very complicated objects. And yeah, I think in general using these complicated mathematical concepts to simplify these gigantic physical systems is very interesting.
Okay. And Robin, I have your questions. I like to. Dear Robin, thank you very much for excellent presentation. Use the Caputo fractional derivative and the Riemann UV fractional derivative. And for example, Caputo fractional derivative, by definition, you have the fractional integral about the f derivative, okay? In the usually I understand you need the function f is a very regular, okay? But for example, you have another definitions about the fractional derivative. It's not necessary to use the f the class one, but you use the sublevel space. For example, W1, yeah. You and the many papers about the physical problems, the many research use the FD class one because very related. But the many research use them so the functions about the sublevel space. But you have the many new properties about this equation. You can comment about this?
Yeah, so of course you need to be very careful in all these definitions on the function space. I think the comment which I had to get used to from my mathematical background also is that typically physics will just assume that your function is indeed smooth enough and satisfies many of the properties that one needs. Simply because if we, think about acceleration and all those things in physical reality, then most of these infinite accelerations which you need for a jump, for instance, they are not possible. In practice, it might happen because of random noise or whatever. But yeah, I think this is something where there's a little bit of a gap between the physics and the mathematics, and you kind of just have to accept and see how far can we still go and use it. Let me see. I see a question here as well.
Yeah, and congratulations, expressivity, and they finish the questions and comments. And the good morning, good morning. It's a very interesting this presentation because I work the fractional operator is so the application. The many comments about the existence in which receive Unix and they grow out in the existence. But it's a very interesting the many models mathematics about the fractional usually the fractional derivative. The last the lecture the Carla about the many problems the situation. And yeah, thank you very much the excellent presentation. That's the contribution to the event, the fractional calculus, the theory events. I believe that
thank you very much.
The next year is continuing this symposium about the fractional calculus. It's very important. The many research the world. Robin, thank you very much. Thank you very much.
Yes, thank you. Bye.
Bye. Ok, thank you. Pessoal, vamos